Well, hello, and welcome you all for our third webinar. And today we'll be speaking about a new way we should look at the energy use of Hawaii, and specifically we are looking at the new Hawaii Energy Building Code. So there's one more. We had already 2 webinars. There's one more left. So next week, please don't forget to log in and be with us here. So again, I introduced already myself last time. I'm Manfred Zapka. I'm Principal of Sustainable Design and Consulting, LLC. And I'm also an adjunct professor at the School of Architecture of the University of Hawaii, where I teach and conduct research. And the type of research I do at the moment, also for the past couple of years, is about energy efficiency in building and occupant comfort. So what we're talking about today is that we show that we need to have a new look at the energy use for Hawaii, and we will be having 4 parts, and so we'll be speaking, where we are at the moment. Afterwards, we think that it's important to get a couple of key terms cleared up, and then we'll be speaking about the new Hawaii Energy Code. So the first one is incentive reason why we change the way we use energy. And there are actually 2 ways. One is that we are pushed, and the pushing is actually from a code or law. So, and whenever we have laws behind us, we think about penalties, and that's the motivational factor. The next one is the pull, that we say, all right, when we save energy, we actually achieve something which is an reward. So both actually are important, and because without both, we do not have the desired results. Here we show a nice figure, which actually Howard Wick let me share. We have the standards for the different energy codes here, where we have this one is the 9075, that's ASHRAE, 90.1. And here we have the IECC. And we see very nicely, relative to the energy use index in 1975, we actually have made a lot of progress. We are here right now, and we are about 55%. In the residential, we are a little bit higher. And so we would like to go even more down with the energy use. And that's hopefully what we'll be achieving when we adopt new energy codes. So the energy codes we have, these are non-voluntary, but we said we are compulsory. And there's energy-related standards, which are non-voluntary and compulsory, but sometimes they're compulsory, but usually they are not. And so, but they also can be like standards, which are not required by law, but they add a lot of value, a lot of meaning to our endeavors to save energy. So, and down here we have two ways to energy efficiency. One is technical, one is non-technical. Here's a map where we are in terms of energy code adoption and implementation. This is the United States. Down here, that's our we. And we see actually we're at the forefront of adoption implementation. And we have the IECC 2015, equivalent or more energy efficient. So there are only a couple of green states here of the union, and we are one of that. That's pretty good. The other thing is actually how are we right now in terms of residential building use compared to the code goals. And then we see the dark greens, they are the most progressive. And then actually the red ones, although we have adopted the code already, we are still less energy efficient than in 2009 EISCC. So we have still a way to go. Here's some major milestone where how the energy code implementation happened in Hawaii. It started in 1978 with the first Hawaii Energy Code, and it was ASHRAE standard 1975. Then afterwards, we went through some iterations here. The first time we adopted the ASHRAE 90.1 was 94. Then actually we upgraded. We were pretty close. 2001, we had but it was only for the city and county of Honolulu. Then 2009, and here right now, that's where we are. We have adopted the new Hawaii Energy Code based on the 2015 IECC. And this one actually is the ASHRAE Energy Code. So let us just speak about the benefits of energy efficiency and energy conservation, and just have a closer look. So usually when we speak about energy efficiency, we consume less energy, therefore we save energy cost. Pretty straightforward. But there's more, because sometimes things are different than we think they are. Because we should actually look at the energy cost savings not only in dollar amount, but they can also have which is tangible benefits, but they have also a wide range of socioeconomic benefits. And these sometimes are less tangible, but nevertheless, they're very valuable. So the benefits of energy efficiency measures, which are EEMs, this is a very useful term, are much wider than the only one in terms of energy cost savings. So we go past the tangible cost and we embrace the socioeconomic benefits. And here are some key concepts about energy efficiency. So when we save energy, something happens, which we had to pay a lot of money. Then we have some kind of energy efficient measures, and all of a sudden we have to pay less money. And then something which has happened, a rebound effect, because when we spend less money, a lot of times actually we increase because we were used to spending this kind of money. So all of a sudden we are spending more energy, and it's almost the same as we have before. Therefore, this one is called the rebound effect. And the rebound effect is the concept, that the expected energy savings from energy efficiency improvements do not occur. And there can come a couple of reasons why they did not occur. Because there might be an increased demand of energy, and they're often not realized because the improved efficiency gains are undermined and counterbalanced by increased consumption and expenditures. Let's say a problem, an example. So we store PV on the roof to save energy cost. And what happens then? Sometimes we can save a lot of money, we got incentives, and then we buy more appliances or put AC actually in order to improve the actual perceived quality of life inside of our building. That's not academic, that also happened to us. We actually gave a lot of kilowatt hours back. So, somebody told us, well, why don't you just get an AC, then you're much better off. That actually happened after, not only because we wanted to have, we don't want to produce more actually that we need, but we needed the AC in order to create a nice indoor environment. The other side is kind of an interesting is, back in 1980, that's actually my car, not really my car, the car I had afterwards, it got 18 miles per gallon. Today, we can have 18 miles per gallon with a big car. So what are we doing? We are fine off because we have a bigger car, it's more comfortable, it flies over the roads. And so we actually we use the same kind of energy. Why not actually having a similar experience? We don't go that high, we don't have an SUV, but we buy a much more fuel efficient car and have all of a sudden like twice as much of fuel efficiency. So this would be the real saving. So the regular criticism, the rebound effect, when energy efficiency does not deliver the full expected savings. So we have to watch that. And when we speak about energy efficiency, this can actually have two different meanings. First is the technical efficiency, in terms of technology, and the other one is non-technical. It's more behavior. Are we actually changing our behavior in order to save energy? Both are actually important. We have to have the technical means to do it. On the other side, we also have to align our behavior. And both of these these issues, both of these criteria are ingrained in the energy codes. So the same with less, less versus more with the same. So same with less versus more the same. What does it mean? Here, for instance, we have the same with less. We are actually using energy efficiency in the houses and have actual tangible energy savings. It could be also something else that we do more with the same. So here we have an energy inefficient house. On the right side here, we have a very energy efficient house. So we basically spent the same or a little bit less or whatever, hopefully, and we have the same kind, we actually get much more in terms of the function, in terms of the experience. So upgrading energy efficiency can mean either less energy is consumed to provide the same level of service, or the same energy is used for this for the higher level of service. Can mean both. And here's actually something which we also have to keep in mind, and which is not necessarily covered with the codes, because how can we consume energy? We can consume energy by just cutting down on the consuming energy, just at the, where at the point in the building where actually we can convert the electricity to some kind of useful thing. The other thing is supplying the energy. Therefore, we would reduce the losses. And typically, demand-side energy efficiency intervention, they receive much more attention, but both sides are important. Here an example. So right now we have like a power plant, we put in like 300 units of energy, and there's a lot of losses. There's like 180 here in our case, about 2/3 is lost. So what we have in our building down here is only 30% of the energy. In the case of Hawaii, it's oil, to use in our house as energy. A lot of losses. We should avoid that. Here's one which is called the cogeneration. This is a way just to increase the efficiency significantly. Same thing here, 300 units go in, but here we do not lose the 180 because some of the heat, because we have a thermal power plants, here in Hawaii we have them all, that we can use some of the heat which we usually would have to create with electricity in the house. So by taking full advantage of these kind of which are they called the combined heat and power, that we can actually increase the efficiency up to 80%. So we see that's not only saving the building is important, it's also like how do we derive the energy? How do we bring the energy to our place? So energy conservation means actually two. This one is that we can use less. We have less energy consumption, and it is measured by the amount of energy saved. Important the difference right now between energy efficiency and energy conservation. Because remember, IECC is energy conservation code. So improving energy conservation, we reduce the absolute benefit quantity of energy which we use in the building. But improving energy efficiency, we are reducing the amount of energy needed to provide a specific energy service. Sounds very academic. It is not. We'll see it right away. So for instance, here we have like an example, when we have a classroom, and I had the fortune just to use a couple of functions, classrooms here on the island, where it was really hot inside. So, the function here in the energy service is to provide a conducive learning environment. Could be also when we're living, but here it's the classroom. So this would actually mean more environmental quality in terms of more ventilation, cooling, lighting, sound, and so on. But all of this actually could use more energy. But the important here is that we save energy in order to offset the additional energy. So this actually is the idea of an energy saving, energy service. So the responsible efficiency use of energy is both. We reduce the amount of energy which we consume in the building, but we improve the quality of energy service. So that actually means, for instance, we have an AC, and the AC is not really, it's not sufficient. We have to have a bigger AC. So we should actually replace the AC unit, not with the same kind of efficiency, but the efficiency has to be higher. So although we might actually save this, we consume the same kind of energy, but what we get out of the energy service is much better, much more valuable. And the third one, we saw that the energy through the generation and transmission, we should also keep that in mind. So in the second part, I would briefly like to go over the energy situation here in Hawaii, because they're so much different from the US mainland. We have a lot of challenges and opportunity, and we see actually what is the current use of in the building, what is the biggest opportunities and challenge. So we are all the way here in the middle of the Pacific, far away from any kind of pipeline or national grid. We are on our own. Compared to the rest of the country, Hawaii is actually pretty good. We are in the 48th ranked in terms of how much energy we use. And here the ranking, we should go down. You shouldn't be up. Here again, like we see, we are the 48th in terms of total energy, and we have a couple of islands which are not connected. Here we see a short diagram how we get our energy. We have most of the fossil fuel here. We have some coal, and we don't have natural gas. Lately, they have started to bring some cryogenic in, and maybe in future we'll have a natural gas here, real natural gas, not like we derive from petroleum, but right now we don't have. Another specific challenge is that, the islands are not connected. So each island has its own power generation. And if we look at what kind of the total energy use for what kind of fuel, it stands out that Hawaii actually uses a lot of energy, much different from the rest of the United States. Here actually we see the residential Hawaii is basically, we have transportation, it's way higher than the national average. And that is because we have, of course, a lot of planes coming in. Here we see one very crucial thing, which we always have to keep in mind, that we are here in Hawaii, we are very much dependent on oil to make electricity. Here we use about 70% of all the energy in terms of making electricity. And on the main, it's only 1%. That actually means the following, that we have 100% of all the oil which is used in the United States to make electricity. 56% of this oil which is used to make electricity in the United States is used here. So it shows how much our dependence is on Hawaii, and right now we can really appreciate how the government here and all the agencies are pushing us to wean us of oil. Here is like the energy use in terms of how it is in the residential, commercial, and other parts of the economy. We see here the residential is about 1/3, commercial is much higher, and then we have other. Here's like how actually in a residential, typical single-family home, the energy use is distributed. We have about 45%, which is related to the house design. So when we build a house, the envelope, we put cooling in, we water heater, lighting, and so on. And the remaining 55% is dependent on what the behavior of the occupant is. Because the occupant basically decides what kind of blinds they buy, what kind of electronics, and miscellaneous. In commercial, it's much different. In the commercial, 83% of the energy used in commercial buildings comes with the house, so to speak, and only the rest is behavior. So it's a big difference. So therefore, residential and commercial buildings is like two different things. One good news is that Hawaii has made a lot of strive to have renewable energies, and right now we're actually up to 21%, and we see here the mix, and we can be proud of it. And this is really very important for us. Here's a very nice graph, and that actually will show you something. It sounds difficult, but you always have the opportunity to go back and see the recorded webinar. Here we have the different streams of energy. The thicker the stream, the more energy. One of the big thing here to see is like here on the right side, and I press that we can see it. This one is the energy service. This is actually the energy we can use to put in real use. Whereas the rejected energy, we don't have use. We basically here in Hawaii, we're heating up the ocean. And if you look down here, that about only a little bit more than 30% of the energy which comes into the state, which we derive from here, or it's in the state, we are using. And about 2/3 or more than 2/3 actually goes to waste. We should change that. This is like you know, something which shows you which gives you an idea how the electricity is generated and used. Here, this is very typical, but it's only for information. So we have in the morning, the evening, we do not consume a lot. But in the middle, or there's some kind of a peak electricity demand where actually the demand is the highest. And that's actually this demand we have to satisfy with power plants. So if we have renewable energies here, like we are shaving off sometimes, specifically like, you know, this is in the middle of the day when the sun is the hottest. So we actually we save here a lot of electricity, but the problem is that, you know, this one remains. So the peak power which has to be provided by a power plant. So this is important that you know, like the average cost of electricity usually, so 80% is fixed cost. So even if we do not draw anything, you know, in terms of electricity, we still have to pay for the power plants. And this comes actually, we see this right now, this might come with a little bit of a, you know, a sour apple here with renewables until we have figured out, and we should, and we will succeed how to use renewables in the best way. We have the problem that, you know, the prices might not go down considerably. On the contrary, it might even go up because it is not easy, for instance, for HECO also to manage this kind of demand. Here's actually where we want to go. And you see all these residential, commercial, other, up to 2030. We expect that, you know, the residential energy demand will actually outweigh the commercial increase. This is the increase of the relative to 2012. So since today's discussion about the energy code will be mostly about the residential, we keep this in mind. This is really a big nut to crack here, and we actually have to be very conscientious. We have to use all the things we have to have, including the energy code, to make it happen, to decrease and hold it in check. Again, here the biggest predicted increase in energy is in the residential. How are we going to handle all this energy in the future? So it would actually go up here, the red line, that's would go up. So what we have to do here is that we have to bring it down. This is the savings. So we have to actually bring down. So this actually is our challenge, where we have existing energy codes and standards, the blue one. The other one is economic potential, savings from all cost-effective measures. And here a lot of things are beyond code. So that means, you know, we actually have to entice people. We have to show them incentives in order to help. Energy code is very important, but it's not all. So the challenge for Hawaii is we'll have to lower the energy. We have to save energy and lower also the greenhouse gases, but we also have to lower the peak power load. Both of these are very important. So this actually brings us to the third and to the fourth and last part, where we will spend the rest of the webinar. And we would like to get an overview of the new Hawaii State Energy Code. And the new State Energy Conservation Code is based on the International Energy Conservation Code. And it is from 2015. And it actually comes from the international association here, the International Code Conference. They basically also have, they are producing a lot of codes, not only energy. So building code, fire code, all kinds of codes. But you know, the energy code right now is important for us to help building design to get better. So the energy code is something which is called a model energy code. So as we said, like the International Energy Code Conservation Code is actually a model energy code, which is the same everywhere. And it is geared that people can use it, and different governments, different localities, different counties, states, and so on. Here in Hawaii, we added something which is called the Hawaii Amendments. So we added something to the International Energy Code. So that actually made our Hawaii State Energy Code. And it's been already in use for the statewide, but the county-wide is not yet. So we actually are waiting almost, whenever it comes, we said second part of the year. If we look at the zones, we have a couple of zones here defined in the 2015 IECC. It's the climate zones, which actually gives a representation of what you should expect from the climate. And here, of course, like the zone number 1 includes Hawaii, Guam, Puerto Rico, and the Virgin Islands. So with Hawaii, we are down here. We joined all the people here at the very tip of Florida. And there are a lot of major standards referenced and that is sometimes when you start using the energy code, which comes to a big surprise, because these are not even all of them, there are much more. So, so they are actually referred from the IECC 2015. So here, for instance, we know ASHRAE, we know IECC, we know the National Fire Code, the IEEE. So AAMA, this one is defining what kind of cooling we have, and ASTM, and so on. So in the 2015, it does not delineate all the details, and again, it usually refers to these other codes. And here we have the ASHRAE 1990.1. That's the National Model Code for Commercial Buildings, and the 2015 IECCs for the residential buildings. But in the 2015 IECC, there is more than only ASHRAE 90.1. So we adopt and implement the energy code, then it becomes the model code, and then we have specific amendments. Here we can have amendments statewide, or we can have it county-wide. It is actually good to see, or interesting to see, that the US does not have a national energy code. So the jurisdiction of all the energy code is only locally. We have two parts of the residential energy code. One is, again, like this is the model energy code on the left side, the IECC 2015, and Hawaii amendments. So the Hawaii amendments basically says that we have to follow the IECC 2015 plus certain conditions. The conditions here, right now, we're only speaking about the residential. It goes in different chapters. Definitions, general requirements, for instance. Then mostly we are right now concentrating on chapter 4, the residential energy efficiency. Then we have one chapter for the existing buildings. This one is for the new buildings. And then the reference standard, which we already addressed. There are many. And we have two appendices. And here, like the solar ready provision, we would like to have the conditions conducive so we can add a PV solar, so we can achieve net zero in the future. Here's the section 4, which I said like is the most important for us, where we have the different sections, R401 to R06. And here we have, the tropical zone. These are the compliance part, and we have 4. We'll be seeing this later on. And we have the tropical zone, which is general, it's a prescriptive, which gives a very unique requirements for Hawaii. And there's some actually delineated also in the IECC 2015, but the tropical zone is very specific for Hawaii because we added certain amendments also in there, certain requirements. In the prescriptive, when we see a prescriptive, means we prescribe. We go down a list and we have to follow all the things. So in the prescriptive, we have the building thermal envelope, we have systems, and we have electrical power and lighting systems. These are three major elements which also have each got one section in the IECC. Then actually what comes with the 4 or 5 is the performance simulation part. This is a compliance part. Again, here, the first one would be we have to comply to the tropical zone standard, which is like a prescriptive. The other one is also prescriptive, but it's not tropical zone. It's whatever is outside of the tropical zone and the requirements. The fourth one is the performance, and that actually says if we use certain performance metrics and if we meet them, we have attained compliance. Okay, this one, the performance is simulation, and the last performance is ERA. This is the energy rating index. Here we have a short look at the commercial, although we are not going to speak about the commercial here. And this is the reference code. This is the ASHRAE 2015, 90.1. We have the prescriptive compliance part and the performance. We actually have 3 here for the commercial. On the other side, the residential, we have the prescriptive again. We have a performance, but here we have 2 kinds of performance and the tropical zone standard. And we can attain code compliance by selecting and satisfying one of these compliance pathways. Again, we said like we are looking at the residential part of the IECC. We have the prescriptive, the performance, and here we have like energy use, energy simulation tool, which we have done like a lot of that recently at the University of Hawaii. And we have like what is called the ERI, but with the HERS standard, which is a rating for residential buildings. In this performance, it says that if we use a simulation tool, the energy cost of the things which we want to propose have to be either equal or better than the standard reference design. So they give us a standard. We can prove it in a simulation that this one is the standard, and then we have our proposed, and the proposed in terms of cost has to be low. And it's a very neat way of achieving compliance because it allows us a lot of flexibility, which the prescriptive doesn't give us. So the second one would be the ERI or the HERS score. If we prove that the ERI score, HERS score is equal or below 52, then we also compliant. And the difference between the simulation tool and the ERI is that at the simulation tool, we do not account for appliances and so on, so they keep outside, whereas the ERI does. And again, like the third one is the tropical zone. Let's go through a couple of, quickly, a couple of examples here. So the section 4.2 is the building thermal envelope. The thermal envelope means as if you have put a code around the building, and then the code is the envelope. And the objective here is to reduce heat gain, and we speak only about heat gain because we're in Hawaii. And we should reduce the heat loss, because if we have an air conditioning inside, we actually we should conserve power by not cranking up the AC so much. And but we can do it too. First of all, we reduce the heat gain, and then we have to get rid of the heat. So we have to pump it out, so to speak, and we can do this either by an HVAC system or with the adaptive without the mechanical cooling. This would be a naturally ventilated house. So here we don't have any kind of mechanical ventilation or mechanical cooling. And here, just very briefly, what kind of requirements? We have to have a vapor barrier in the envelope, and the vapor barrier avoids that humidity gets into the structure. We have the so-called R value. Probably everybody heard that. And the U value is just the R value, 1 over the R value. So this is U value and R value are very closely related. And the specific insulation requirements is for attics, ceilings, access doors, walls, all kinds of stuff here. And I just wanted to point out that, you know, we are not making a lot of detail, you know, description of the IECC and how it works with his colleagues at the energy office from the States have done a wonderful job of just providing very specific workshops, which is like one day. We just wanted to give you an appreciation of what is coming out and how we actually have to be prepared in order to use the new energy code. Again, in the building same section here, we have fenestration, which is either windows, doors, or skylights. So there we have to have certain metrics here, which is the U factor, SHGC, like solar heat gain coefficient. And one of the big thing here is also air leakage, that if we tighten up the envelope, so we avoid hot air coming in or cold air going out. And we have a maximum of fenestration, the U factor, and the solar heat gain coefficient. So this is the building envelope, and the building envelope actually, if we're holding something, you know, outside of the building, so we actually save it. I mean, we shield it basically against the elements. Here's section 4.3, the building section. These are things we are, you know, directly using energy, or where we can, if we configure them, we are saving energy. Here, for instance, hot water, where if we insulate hot water pipes, we can save energy. We can save energy by having like very effective fans, and the ducts have to be either insulated or they shouldn't leak. We have equipment sizing, efficiency rating, so we should always get a very efficient AC, or we have, for instance, pool or permanent spa or any kind of pumps which we have in the house. So these are how it's system. So when we go through the prescriptive, what we have, like the 4.3, you have all kinds of different prescribed requirements. So this is the prescriptive way of approaching things. Controls, we have the hot water boiler, ducts, whatever we saw in the preceding picture. And in the section 4.4, it's a very short section. We say like this is electric power and lighting system, and here is it very clear. You have to have a lot of, you know, very effective lighting. So there has to be high efficacy lighting. And either lighting is so advanced, so it's really nice to see. Either you have CFLs or LEDs or other kinds of high efficiency lighting. And that makes a big difference. And we see it, you know, when we go somewhere, this is the incentives of them are very, very high and very direct. So we have the performance base, what we said, like we can have it like through a simulation or the ERI. And they are defined in the section 4 or 5. And that basically lays out what we have to go. Again, like it's very flexible. We can make a simulation. We can step away from the prescriptive and just be, you know, the architect can be all kinds of, you know, use your imagination. But of course, there are certain things which we have to do. It's like mandatory when we do the simulations. Here we see like the section 4.5 and 4.6. Again, this one is a simulation, energy simulation, ERI, and it shows, you know, what the criteria are here, that the annual energy cost has to be either equal or lower than the standard reference design, the SRD. In the HERS, we have to have an index which is 52 or less. And here, very important, see that the simulations under the 4.5, so this is the simulation-based prescriptive part, compliance guys, sorry. We do not we do only look at the building envelope and the systems and so on. And in the HERS, actually, we look at all these things, but we add appliances and miscellaneous loads. So that's a difference in terms of compliance. We can, of course, also simulate appliances and miscellaneous, but it is not part of the compliance part. So how can we check this? As either the house energy simulation software, and we at the University of Hawaii, we have used BOPT. It's one very easy, the best is it's free. You can use that simulation program. The other one is the appropriate method of score determination. It is something which is like an online tool rest check, where we can see how much is the ERI score. Again, like if it's 52 or less, then we are good automatically. Let us just very briefly look for something which is very unique to Hawaii. And this is the tropical code compliance part, and this is the prescriptive part. And it has a very specific requirements, which we just go through here briefly. So here you see this wonderful house at the beach, very tropical. Why not using this if we can? If we have enough cross breeze, if we can cool it, if we don't have too much solar gain with these big overhangs here, this is a wonderful thing. And we should use it. So going down the requirements, the first one is you cannot have more than 1/2 of the occupied space can be air conditioned. All right. And the occupied space is not heated. I mean, we usually don't need, but the code is actually defined also for certain elevation. So it could be getting cold, but we cannot use any kind of heating things. And these are the same as in the 2015 model code and in the in the amendment. So here we have the amendments, here the model code. We have to, the IECC says that we have to have at least 80% of the energy for water heating comes from solar and renewables. And here under Hawaii, we have to have 90, so we're more stringent. Next one is like the glazing. And here the specifics here is like the, this is the solar heat gain coefficient. And this determines how much sun is going through the windows. And we actually try to get as much direct sun out, like hot air and cold air. This is one different, but here's like how much goes through, how much of solar radiation goes directly through the window. And here what we have is a shading, a projection factor that is just here. You make this distance here divided by this, and this one is the sill of the window. So the idea is here that if the sun rays come, that they are shielded, that the window is shielded. We have other ones like skylight. We have, lighting, what we have to have in the model code. And we have here that, there's certain roof surfaces. So the roof has to have a certain configuration. And here, for instance, we have, a certain slope on the roof. The operal fenestration, provides a ventilation area equal or not than 14. This is basically, we do not want to have a mechanical ventilation where it is not required. On the tropical zone standard, it is not required, but in the regular IECC, it is required. And this is actually an example where from the IECC, if we apply it, we will be using more energy because of mechanical ventilation requirement. But on the other side, we increase the comfort and indoor air quality of the building. So we have here an example where actually an energy conservation code requires us to spend energy in order to make things better, to increase the value of the energy service. All right. And here it says some other ones that bedroom, for instance, with exterior walls have two different directions, operable fenestration or windows. That we have to have some kind of a cross beam. You probably all know if you only have one window at one side and there's no cross beams. And interior doors have to be, capable of being secured in open position. Just put a thing in there, and so it doesn't close. It's very easy. And here, the ceiling fan it's really important that we would like to have ceiling fans in buildings. And well, we have to have at least the rough end. And so it means we don't have to actually install it, but it has to be made very, very easy to install it in the actual house. And then, for Hawaii specific is the jalousie windows. They're not the most effective, but, they're such that, the modern ones are better than the old ones, that you have to have some kind of not surpass a certain ventilation rate. And we have some other things here, like that the walls and ceilings separating air-conditioned room have to be almost the same quality as exterior walls. And that is due to the fact that we do not want to have any kind of moisture propagation through that. So just summarizing, we have certain, code compliance pathways. We have prescription, we have the performance. That's actually what we like here. What we have found this is a very nice tool, not so much used right now, but you really should use it. So it gives you a lot of flexibility for the design. We have the ERI codes and we have tropical zone standard. So just summarizing what we have learned, we have learned actually the difference, the very important difference between energy efficiency and conservation. Remember, conservation is you have to save a lot of a certain amount of energy, whereas the energy efficiency is you should be much more efficient in order to use the energy in a good way for the energy function, for the function why we have actually using energy, like it could be like ventilation, it can be AC, it can be a vacuum cleaner, refrigerator, whatever. So, and then we've seen that it's a very unique situation in Hawaii. We should really keep in mind, we use a lot of oil, we use a lot of imported oil, and our incentive in order to replace this or wean us from oil just going different ways is very, very acute indeed. And then we have to discuss the basic of the new Hawaii Energy Code. So thank you very much, and please join us for the fourth webinar in the next week. And we'll be discussing the importance of combining energy efficiency and healthy buildings. So that's a very important and timely thing. And we'll be sending out a survey, and please be sure that you send back and thank you very much, everybody. And it's been a pleasure, and see you next week.